I will first say that it's really sad and strange to be in Lyon. This is the first time I've been here many times, and this is the first time I'm here so that Krzysztof is not here. But it's also a pleasure to be in this conference where we have so many of his friends and we can share our memories. I will not now share much memories. We decided, or the organizers decided, that there's supposed to be some talks about Krzysztof's scientific career, his results, basically. And that was given to Denny and me, and we thought that, okay, 1 hour is good for that, but of course 1 hour is completely hopelessly inadequate. Is this the... And how does that change? This one. All right. Okay, so let me try at least concentrate a couple of things. So, won't go much to the history, it was already mentioned. But one thing which was clear already now, that Krzysztof was a true Renaissance man in the sense that he was active in very many fields. Here is a long list which is still very partial, and this doesn't mean that he just scratched the surface of these fields. When you look at the history of his work, it really goes into periods where he concentrated long time, very deeply, and I would say that deeper than anybody else in that field, in that particular problem. And one way to periodize is maybe here, although the longer you go in this list, the more, of course, he is going back also to the works he was doing earlier. But I'm too far. Okay. So let me start immediately with the first. Which one could call it geometry and physics. So this took place in Poland. So he got his PhD with Krzysztof Moran. Krzysztof Moran was a person many of you, at least older ones, know, who built basically this Department of Mathematical Methods in Physics in Warsaw, which produced a long list of very well-known scientists. And from Krzysztof, I always heard that he had great appreciation to Moran and to this environment. If you ever were there, at least the times, I was there, the first time I was visiting there was around 1981. It was an industrial backyard, basically, a semi-industrial building with an elevator which was used to sort of heavy duty, like several ton objects. And everything was run down, but it produced a fantastic environment. And especially for Krzysztof, he was very appreciative of the following people. Jerzy Kijowski was basically studying at the same time as him. And of course Moran, and then the most intelligent person in the world, according to Krzysztof, namely Stanislav Voronovich. So what he did during that period was geometric quantization, which was sort of in this geometrical world of Moran and company, was sort of one of the topics which people were doing. And he was there. The problem, if you know about the field, is that you have this nice picture of quantization, geometric picture, but then you have to choose a polarization so that you get the physical Hilbert space. And that was a question, how does that, what is the dependence? And it was sort of an unsolved problem, and probably until now. Another subject which was mentioned already before was supermanifolds. So actually Krzysztof has the basic structure theorem on supermanifolds. Supersymmetry and supermanifolds were, of course, very popular in physics in the early 70s, starting from the early 70s. And he has the basic structure theorem. It was probably very much ignored and forgotten for a long time. He himself was very sort of played it down. Actually, when I met him the first time, slightly after this period, he was playing down all of that stuff that he was doing then. This theorem became very sort of well appreciated much later in the 2000s in superstrings and in the third or nth superstring revolution, whenever it was. And geometric quantization also, which was not mainstream that time, became mainstream maybe 10, 20 years later. So he was certainly in his work here ahead of his time. Nevertheless, well, here is his thesis, actually his habilitation thesis of Fourier-like kernels in geometric quantization. But of course, at that time, the biggest fashion in mathematical physics, at least in rigorous quantum field theory business, was constructive field theory. It was done basically, people like Gleeman, Jaffe, Spencer, Froelich, Simon had constructed super normalizable field theories. And Krzysztof was very eager to leave his previous life and move into this field. And of course, being in Poland those times, okay, was you were not in the center of the world, and it was really challenging. There's nobody to help you; you just had to read papers. And he decided to choose a problem because he heard somewhere that there's a controversy among the mathematical physicists about phase transitions. Namely, Gleeman, Jaffe, and Spencer had proved that if you take a double well potential, then of course you expect there to be a phase transition. Of course you had to work hard to prove it for the continuum limit. But then it was debated whether if you take a triple well, whether the renormalization of Wick ordering screws up things so that you won't have any more three phases. Krzysztof said that this is of course nonsense. Of course, doesn't screw it up if you do it correctly. He did it correctly. It was a big work in which he learned all the tricks of the trade and expanded them. And he also came to the conclusion that to make any progress in this field of rigorous renormalization for physically interesting theories, you need to study what was taken for granted in physics, namely renormalization group. And that is the time when I met him. Here is the first time I met him in Cargé, 79. And we were basically both going to be in Harvard, me as a postdoc, he as an instructor in the following fall. And in this conference in Cargé, we decided that we should really learn renormalization group and use it to construct the field theory. And let me say a couple of things what was achieved in that. So just the basic background, which is nowadays completely textbook material, the Wilson and Kadanoff approach to quantum field theory. You are describing field theories by effective actions, describing the physics at the given scale. So, and then how these things depend on scale is given by the renormalization group flow. So the flow of how physics changes with scale. And in this picture, you expect that in the infrared and in the ultraviolet, you will be at the fixed points of this flow and exhibiting scale invariance. This also shows you that if you become non-interacting either in the ultraviolet or in the infrared, then you have good chance of trying to actually mathematically construct such a theory, which usually are called asymptotically free theories. So that was what Krzysztof and me set up to work on. It took several years, maybe six years. In the end of the day, maybe these are the main results. So there was an infrared case, namely the familiar 5-4 theory, which you put on a ultraviolet cutoff, so put it on a lattice and ask how does it behave at the critical point. And the ultraviolet problem, convenient case was a two-dimensional fermionic-Gross-Nouveau model, which is asymptotically free in the ultraviolet. And in both cases, then we show that the long or short distance behavior is given by the corresponding free theory. There was even a construction of so-called non-renormalizable theory in 2 plus epsilon dimensions by changing a little bit the covariance of the free path. Let me comment a little bit what we actually did. So, of course, how do you go on doing that? You start sort of in the ultraviolet problem. You start from some scale L, and you start increasing it incrementally, say multiplying by 2, for instance. And then in the end, you want to take the starting scale to 0, and in infrared, you do the opposite. You fix the starting scale and take the ending scale to infinity. So in the end, you just need to control, in general, one such map where you go from scale to twice the scale. And that's given by a functional integral, which has both infrared and ultraviolet cutoff. And if you go to dimensionless variables, you have infrared cutoff, say, 2, and ultraviolet cutoff 1. So this is a problem of classical statistical mechanics in the high temperature region, in principle straightforward, and that was the mathematical problem to control that, so that you can iterate actually the map. And if you do that again in physics books, then when this is discussed, it's observed that what you get is basically even if you start with something nice and simple, like in the first line, you get arbitrary many-body interactions later, and then your job is to isolate a finite number of relevant and marginal ones, which play a role, and then the rest should be irrelevant. And then you fine-tune the relevant and marginal couplings to get the quantum field theory, or the relevant ones to get the critical point. Familiar story. But to carry it out was not a piece of cake. First of all, the series here it has the usual problems of perturbation series. It doesn't originally converge. We showed actually that once you do things correctly, it converges for small values, so the field's not too large. But then there are large values, so-called instanton variables, which you have to introduce in order to take care of them. And combining these two pictures together and putting something which you can iterate your transformation was complex, to put it mildly. Complex proofs which exhausted the two of us in the end. And it sort of exhausted a lot this thing also on the numerical side, because if you try to really do a normalization group numerically along these lines, so usually one introduces some approximate renormalization group scheme, gets some results, and then you would like to improve by adding some terms. here it's not obvious what to add and how to parameterize. We did it rigorously with our variables, but of course, if you want to go to non-trivial fixed points, then that will be challenging. And this is sort of still a problem. If you compare it, for instance, with conformal bootstrap, where this can be successfully done. I mean, there's a way to introduce more terms in your setup so that approximations improve, and that wasn't the case so far in the renormalization group. Anyway, for Krzysztof, I think he certainly was very tired about doing these long proofs. But in particular, what happened was the first string revolution. We were both invited to Harvard to give lectures on our work there. And that was just the time when everybody in physics jumped into strings. Nobody could be less interested in field theory. And Krzysztof in particular took that very sort of seriously, and he decided that now it's time to change fields again. And in some way he went back to his roots when he started his work on Wess-Simon-Witten model, and that's what Denny is going to talk to you about in a moment. So what I will do now, actually I have no idea when I started, Jean-Michel. 15 minutes ago, perfect, okay. All right, so he jumped into his second period, which was the conformal field theory, which he dug. I was involved in that in the beginning, but later he really went very far and did extremely nice work, which you're going to hear about. But so came the time again that he felt that he had sort of understood something well enough in order to dig something else. And it was a time I was supposed to organize a semester in the Mittag-Leffler Institute. It's a math institute in Stockholm, close to Stockholm. And I was desperately thinking what would be a nice subject. It was supposed to be something around partial differential equations, which I found a bit boring. And then I thought, we discussed with Krzysztof, and he said, what about turbulence? And of course, none of us knew anything about turbulence. We had heard that maybe that Polyakov had at some point worked a little bit on turbulence, but that was it. And didn't even know the people, but in the end, that time you didn't even Google, but somehow we found sort of some people whom to invite. And luckily we invited Itamar and Uriel, Itamar Prakacha and Uriel Frisch, and a couple of other people like that. And even better, this was just the right time for people like us to jump into turbulence. Because that was a time when very sort of field theoretical minded people like Grisha, for instance, Grisha Falkovich and several others were interested in this subject, and also there was a nice model to work with, going back to Robert Krajnan already a long time ago, but it sort of became, by his article around those times, very intriguing for people. And so this is a simple linear advection equation where you have a scalar quantity like impurity, pollution in the atmosphere or something like that, which is advected by the velocity field, V here. There's some diffusion, molecular diffusion, diffusion constant, and then some source of the pollution. Source in the large scales, the velocity should be turbulent velocity, but Krajnan took it synthetic. He took a Gaussian velocity field having similar properties as what you expect from turbulent velocities, namely Hölder continuous velocities. And then the question is, what is the statistics? So you have this equation for the time-dependent field, driven by a noise, Gaussian source in large scales. It should settle to some stationarity. And how does it behave? Okay, in particular, how do so-called structure constants, namely, that's the sort of correlation you are interested in turbulence, when you look at the field at nearby points and take moments of that random variable, how do they scale? All right, so what we showed with Krzysztof was that actually the statistics is intermittent, meaning that the moments don't scale in an obvious way, the n dependence, n being the moment you take, and there is a non-trivial multifractal spectrum. So in particular, naive Kolmogorov type scaling picture, which you could apply to this model, the kind of picture which Kolmogorov introduced in Navier-Stokes, actually is violated here. You have anomalous scaling. And our proof in 2 lines was that once you have this equation here, it's obvious from the field theoretical point of view what you want to do. You look at the Schwinger-Dyson equations, which are easy to derive here. It's a linear equation, so there's a linear operator, and then if you look at an endpoint correlation function, there's a linear operator acting on it, and then some stuff coming from lower order correlations because of the noise here. And the linear operator is determined by the covariance, the statistics of the field. And then everything is in this linear operator, and in particular in its something, it's basically it's 0 modes. The ones which later in a paper with Denny and we called conserved structures or slow modes of the motion of the problem. So doing this, you could actually in the limit when the velocities are very rough, you could actually compute these exponents and show that you actually have this anomalous scale. Sort of important picture which emerged from this, and this is really Krzysztof's nice idea here, namely, which could be called spontaneous stochasticity. So you look at if you look at this advection of the scalar quantity, you could look at it from the particle point of view, so Lagrangian trajectory. So you have something going with the motion of the field, of the velocity field, and in the limit, when you take the molecular diffusion to 0, you have a deterministic equation. If you fix your turbulent velocity field, you have an equation x dot is v, and of course the velocity is rough. And what emerges from the analysis that the solution of this equation is actually not a deterministic trajectory, but a whole distribution of trajectories, a probability distribution of trajectories, which is called spontaneous stochasticity, which is sort of something which is, again, a lot later. Nowadays, this is a very fashionable subject in mathematics, but I think in turbulence, this also was sort of in the air at that time. Still to continue a little bit with the scalar before I had to finish. There was a nice picture with Massimo Vergasola and Krzysztof. They looked at what I explained was for an incompressible velocity, so divergence-less velocity, but you can add some divergence to it, some sources to it, and put a coupling constant to it. And then there's a nice picture, phase transition. When you are small compressibility, you have this explosive separation of trajectories, you have direct cascade of energy, you have intermittency and what's called dissipative anomaly. And once you are in the above the critical point, then you have the opposite, implosive collapse of trajectories, inverse cascade of energy, and energy dissipated by large-scale friction. So, nice picture. Again, something which, of course, one would like to understand beyond the toy model, but it's nice to have these toy models where you can actually, which are non-trivial enough so that you can come up with examples of the things which you might want to do for more complicated cases. Maybe I won't say more about this. Krzysztof, we still continued working together on and off. One was related to KM theorem, as was mentioned before, but maybe the amusing thing here was that you can sort of study the KM theorem again using the renormalization group, and what happens there is that basically the expansion which I gave you, there are none of these instanton variables, to put it in one line, and things are particularly nice and simple there. So that was sort of in contrast what things were in the quantum field theory case. But let's not go to that. Let me just finish by saying a few words about. I've known Krzysztof for 43 years, I think, 42, 43 years. And we became colleagues, and instantly we became friends. We became really very good friends. We were calling each other half brothers. Here's some happy occasions in the 90s. And the second last time I saw him was about a year ago. No, a little bit more than a year before his tragic last struggle started, in happy circumstances in a conference by the Mediterranean. Here, Krzysztof is still in full strength, both physically and also he gave a nice talk to young probabilists on his recent activities. So let me finish and go let Denny to continue with what our friend was up to during the other periods. Okay, thank you.